Okay. So welcome everyone to the third session of our workshop. So Rajesh Jayaram is going to tell us about data-dependent analysis for Earth movers distance.
So thank you so much, and thanks again to the organizers for having me here. Excited to be back at Simon's. So this is the title of the paper, but the title of the talk, as I had it, was a log S approximation for nearest neighbor search for Earth mover distance. So the latter is actually what I'm going to be more relevant to what I'm actually going to talk about today. But I just wanted to leave the title here because this is actually the title of the paper. So this is joint work with Eric Weingarten and Tian Zhang. I don't know where Eric is. He's here somewhere. There he is. So yeah, so let me tell you first about what I'm actually going to focus on. Oh, it skipped. Okay, what I'm actually going to focus on in this talk. So this talk is going to be about nearest neighbor search for the Earth mover distance metric, and in particular, I'm really going to be focused on this connection, this really interesting connection between Earth mover distance over high dimensional points and this technique called probabilistic tree embeddings. So even though when you actually end up solving these problems, you use a tool called locality sensitive hashing. Some of you may be familiar with it. We're not actually going to talk about LSH in this talk. I'm mostly going to focus on the connection with probabilistic tree embeddings, because that's where a lot of the new techniques lie. In particular, there's two main things, developments I want to talk about. One of them are these so-called data-dependent probabilistic tree embeddings from this paper with Shi Chen, Amit Levy, and Eric Weingarten from Stock of a couple of years ago. And this technique is very good at handling one EMD computation, like one comparison between two sets of points for EMD. And the main new result I want to talk about is sort of what I'll call an extension lemma, what's going to allow us to extend this result to multiple computations, which is what you need for nearest neighbor search, where you're trying to search through many sets. So this is what I'm going to focus on today, and let me now define some of these things. So I'll begin by defining the Earth mover distance. So this is sort of a classic metric. I like to think of it as a meta metric because it's a metric over sets of points living in any other base metric space. So the way we're going to set this up is for this talk, the base metric space is always going to be d-dimensional space with the L1 metric. We use L1 because it's a little bit more general. You can embed LP norms into L1. So for the rest of the talk, the base metric is d-dimensional space with the L1 distance. And the Earth mover distance is over sets of points in that space. So if I give you two sets of points, A and B, each of which, let's just say for this talk, have the same exact number of points, S points in each of them, then the Earth mover distance is the cost of the minimum perfect bipartite matching between the points in A and the points in B. So it's the minimum cost of taking each point in A, matching it to some point in B, and then the cost of that matching is the distance in the underlying space. So perfect bipartite matching, but the distances come from a metric space. So you have triangle inequality. It's a little bit more structure than the general problem. So in this talk, I'm focused on the problem of nearest neighbor search for the Earth mover distance metric. So in the approximate nearest neighbor search problem, I have some metric space X. For us, it'll be the Earth mover distance. And my goal is to give as input some data set D consisting of n points from this metric, pre-process that data set in a way such, using some data structure, in a way such that I can handle, given a query, very quickly return to me a nearest neighbor of that point. What I mean by that is I want to return a point which is with a most factor C further away from my query than the nearest point in that data set. If I ask for the true nearest neighbor, it's going to be difficult to do that in time faster than a linear scan over every single point in the data set. But I'm hoping to actually give an approximate nearest neighbor much faster than a linear scan. That's the goal. Very fast query time and not too long pre-processing. So one sort of just like conceptual note is that when we talk about nearest neighbor search for Earth mover distance, a single point in the EMD metric is a set of points in the ground truth and the base metric. So when I say a point in EMD, this is actually referring to a size S subset of d-dimensional space. So this could be our input. These are three different sets, A, B, and C. Each of them is a single point in the Earth mover distance metric and consists of S equals 4 points, let's say in the plane for now. And I want to pre-process these points so that when a query comes, I quickly find the other set, which is closest to this query under the Earth mover distance, under this matching distance. So this is just sort of a conceptual note, is that remember we're talking about a point in EMD is actually a set of points. And so this can cause some confusion. Motivate what? The usage of EMD? Well, so there's a lot of different motivations. One of the reasons that I study in particular is that this is very useful for looking at embeddings of text. So when you have the way we actually study document similarities, we often take the words in the document, we send them through a transformer model where all the words attend to each other, and then each word gets an embedding, let's say 128-dimensional vector, which is contextualized and knows about the other embeddings. And then we want to model how similar are two documents. And the way you can do that, there's multiple ways you can do that, but one of the ways you can do that is looking at this optimal transport. For each word in one document, is there a word in the other document that roughly matches up to it? There's other ways this could be used for query answering, and this is actually the state of the art. There's a benchmark called the Bear retrieval benchmarks for information retrieval, and the state of the art methods for this do actually use multiple embeddings per word, and they embed the query and then they embed the document and they try to find the document which is most similar to the query. So this is actually the problem of retrieval for multiple sets of points is actually a very practically relevant problem. I should caveat with it, in that particular, the second application, they don't use Earth mover distance. They use the version where you relax the matching constraint. But that's sort of happens for Robbie. I'm happy to talk about that offline as well. But there's many cases where this shows up where these points are actually embeddings computed by a neural embedding model. So let me now talk about what our goals are going to be. What is the parameterization for this? I'm going to write this EMD-SRDL1. This is just the notation for the metric space of Earth mover distance consisting of S-sized sets of d-dimensional space. So there's two parameters we care about here. There's n, which is the size of the data set, the number of points I want to search over. And then there's s, which is the size of the subset of a single data set. And we want to think about n as being much larger than s, because n is in some set the input size, and s is just the description size of a single point in my metric space. So in general, like sort of morally, we're thinking of n as being much larger than s. We can also think there's easy reductions to show that the dimension and the aspect ratio of the points in the original space are just both some small polynomial in S. So everything is poly S except for n, where n's can be quite large.
So n is the number of sets of points?
Yes. Yeah, it's the number of points in your data set, where a point is a point in EMD consisting of a size S subset. Great. So n, we want n is much larger than s. Yeah. Okay. So I want to start by instead of talking about EMD, I want to talk about a simpler metric and what we can hope to get for nearest neighbor search for that simpler metric. And this dates back to a seminal paper of Indyk and Motwani, and they studied the L1 metric, and they showed like these very nice trade-offs for L1. If I give you a parameter epsilon, think of this as a small constant number, they show that you can get an approximation of 1 over epsilon for the nearest neighbor search problem in L1. So this is L1, single vector in L1, with space and preprocessing time that's nearly linear in n to the 1 plus epsilon space and preprocessing, and highly sublinear query time. So the query time is only n to the epsilon. So you can get this really nice trade-off of roughly n to the epsilon query time and 1 over epsilon approximation. Moreover, this is more or less tight. There's a lower bound in a very general computational model that shows you can't actually quite do much better than this. There's a lot of things reduced to L1. This is a very general result. And so I'm thinking about this as sort of the gold standard. This is what we could hope to get. 1 over epsilon approximation, n to the epsilon query time. That would be great. But Earth mover distance is a lot more complicated than looking at the distance between two sets of points, two individual points in L1. In particular, there's no like very simple algorithm for even computing the Earth mover distance. And so the bounds that we have for this problem are not quite as good. So here's what's known. So dating back to this paper of Indyk in 2004, showed that there's an ANN data structure that gives you the same kind of approximation query time trade-offs, except there's an extra d log s in the approximation factor. So instead of 1 over epsilon approximation, it's 1 over epsilon times d log s. So d is the dimension of the individual points, and s is the size of the subset. So this is great if we're like in the plane, potentially, but as for high dimensional points, like if we're looking at embeddings produced by neural models, these things are usually at least 128 dimensions. That's large for some definition of large. So then later on, Andoni, Indyk, and Krauthammer, they showed how to improve this for the high dimensional regime. They showed you can, instead of having d log s, you can have a log squared s approximation factor. And so when d is much larger than log s, this gives you an improvement. And the main result I want to talk. Go ahead. Yeah. At this point, I'm just omitting the main thing is how small can we make this approximation with the fixed same space and preprocessing. So the main thing I want to tell you about today is a further improvement of this, going from roughly log squared s to log s. So we get a data structure that has these trade-offs, but with a log s approximation times some log s factors. So it's tilde of log s. So this is the main new result, is another improvement. So it's still not matching what you get for L1, but now it's getting quite close. So let me say something about Earth mover distance. As I mentioned, it's sort of a more complex metric than L1 or these LP metrics. And in particular, it's this, you have to actually solve an optimization problem to get to do a distance computation. So like the classic algorithm is this Hungarian algorithm that actually dates back to Jacobi in the 1850s. We can do a little bit faster than that now. We can set it up as a min-cost flow problem. But in general, it still is not a simple problem to solve. And moreover, simple approaches to this problem, like a standard greedy algorithm, are actually quite bad. So Reingold and Tarjan had this paper where they showed even in line where D is 1, if you tried to do the greedy algorithm, like greedily match up points, you could get a really bad approximation. In fact, your approximation could be more than like root n. So greedy is not a good approach in general. And so for this reason, classic sublinear algorithms approaches like local algorithms, things like this, it's hard to use local algorithms for EMD because greedy things don't work very well. So what are we going to do? Well, the classic approach is when you have a very complex metric, and metric space theory is, well, can we embed it into a simpler metric where simple things work? And the classic simple metric that folks use, is these tree metrics. So the approach of all these prior works is take Earth mover distance and somehow embed it into a tree metric. And where now you have a set of points, each point is a node in a tree with the shortest path metric. And it turns out that if you have a set of points in Earth mover distance in a tree, the Earth mover distance in a tree is actually a simple object in the sense that the greedy algorithm is optimal in a tree. And what I mean by that is you can just take all the points and just greedily match them to the nearest point. So I can move them all up the tree, and then whenever they're in the same node, I greedily match them together, greedily and arbitrarily. And I can continue moving points closer and closer together until they're all matched up. And this is the optimal matching for a tree metric. And so that means that if I actually, once I'm in a tree metric, there's a very simple algorithm to compute Earth mover distance. Because there's this simple algorithm, it turns out, and I won't show the mapping here, but it turns out that there's an isometric embedding between a set of points in the Earth mover distance in the tree and the L1 metric. So I can take a set of points in a tree metric, map it to a single vector in L1, such that the L1 distance between 2 points is exactly equal to the original Earth mover distance in the tree metric. There's no approximation loss here. And we already saw that there's these fantastic nearest neighbor search algorithms for L1. So if we can map into a tree, we can then map into L1 and run nearest neighbor search for L1 and have a very good efficiency algorithm. So the goal is, let's try to embed into a tree. That's going to be our goal. So here's sort of the plan. I'm going to try to design some algorithm, which is what we're going to call a probabilistic tree embedding, which takes a single point in d-dimensional space and maps it to a single vertex in a tree. This is going to be a randomized embedding. Then I can just apply this to a set of S points and turn it into a transformation that maps sets of S points in d-dimensional space to sets of S points in a tree metric, thereby mapping EMD over RD into EMD over a tree. Once I'm in EMD over tree, I know I can map that nicely into L1 without any approximation loss. So the question is, what happens here? What is this embedding? What approximations do I suffer by going from EMD over RD to EMD over a tree? And one important note is that this embedding from points to a tree, it can't just have a good approximation. It also needs to be very efficient to compute. Because remember, I want fast query time algorithms. So some people may be familiar with like FRT trees or Bartol trees. These are classic papers that get tight bounds for approximation of tree embeddings. But the embeddings themselves are not very easy to compute on new points that weren't in the data set. So we need so-called efficient tree embeddings. So now let me say something about a class of algorithms that achieves these kinds of bounds. And the first result in this sort of what I'll call these fast tree embeddings is this paper of Indyk, who showed a tree embedding with the following properties. So it's embedding that maps points from d-dimensional space into a tree metric. First, it has the property that there's no contraction of the mapping. So distances in the tree are always larger than distances in the original space. So that's great. And secondly, it has a property that the distances in expectation, remember this is a randomized mapping, the distances in the tree metric in expectation expand by most a d log s factor in expectation. And so this is roughly where the d log s factor comes from the approximation for that earlier work I told you about for nearest neighbor search. So this was then, in the same Andoni, Indic, and Krauthammer paper, they gave a similar embedding, and they showed a slightly different kind of guarantee. The guarantee is if I give you any set omega of exactly 2 s points, you could think of omega as being the union of 2 sets A and B, and I want to compute their distance in EMD. Then I have the non-contraction guarantee, but maybe only with high probability in S, so not deterministically anymore. And I have the bounded expansion guarantee, but now instead of d log s, it's log squared s. So it's a better bound without the dimensionality. And then lastly, in a paper this paper with Shi Chen, Levy, and Eric Weingarten, we showed a similar result where for any subset omega, but now one difference is we're not going to map the entire d-dimensional space into the tree. Our mapping is only going to be defined on the set of points omega. It's a data-dependent mapping. It only is defined on the set of points omega, but it gets a better bound for small omega. So it's non-contracting for the points in omega, and the expansion is only log of the size of the set you're embedding, log of omega. So in particular, if omega consists of most, say, s to the 100, some polynomial in s many points, then this is roughly a log s distortion as opposed to the prior log squared s. So the hope is to maybe try to run this on some polylog s size universe. That's a good that's a good point. There's the expansion is happening over so s here is really delta, the aspect ratio. And then what's going on here is that there's a reduction from the aspect ratio being something unbounded to the polynomial and the size of the sets. So for the first result, you could actually think about this as d times log of aspect ratio. I believe that's the case. Yeah. You could also think about this like on the plane, d is like or a constant. Then it's just like if I'm just on the like k by k grid or something like that, then this is just log of k, the size of the grid length, if all my distances are between 1 and k. But I agree, it's a little confusing. I wrote that here just to sort of coincide with the rest of the results. But there is a reduction from arbitrary aspect ratio to poly S aspect ratio. Okay, any other questions about these results? This is the prior work, and what we're going to try to do is try to use this result for nearest neighbor search.
Between theorem 2 and theorem 3 once more?
Yeah, so there's two differences. First is that these two theorems, the first two, they're well-defined mappings of the entire d-dimensional space into a tree metric. This last mapping, to even define it, I give you as input the set. The mapping itself depends on the set. This mapping does not. The rest of the other mappings do not. And so this mapping is only defined on the set, and the guarantee is a better approximation if the size of the set is small. So the approximation is log of the size of the set you're embedding. So the last one is the only one that actually is data dependent. So I'll call this the data dependent tree embedding. So let me say something briefly about what these algorithms are. Actually, all three of these algorithms are very similar, and they all have the same exact form. What you're going to do is I'm going to take my points in this high dimensional space, and I'm going to randomly and recursively divide up the space. And I'll do this by like creating random cuts in the space, random grid cuts. And when I create these random divisions of space, this creates a recursion tree. Every time I cut space, I recurse into the two or more component parts that I've cut into. And so for a point in the space, you can imagine it tracing a path down the tree, this recursion tree, corresponding to what hypercubes, sub-hypercubes it ended up in as you recursively divided the space. And at the end, you map a point to the leaf node it goes to. Eventually, you'll get to a leaf node that's like a single point. And the idea is you're going to now want to define edge weights in this recursion tree that you've set up. So in such a way, such that the shortest path distance between points in the tree is a good approximation between the original distance of points. We're trying to preserve the distances. Go ahead. Well, if you imagine that, like, say that all the distances are between 1 and delta, then after like log d times delta cuts, there's only like one. There could only be like 1 point per. Yeah. So I mean, in the limit, you infinitely divide things up. But like, if you have like if you imagine your points come from integer coordinates between 0 and delta, then after a certain number of cuts, you surely split everything up. So this is a well-defined mapping for all points in the space so far. So the picture looks like this. If I have some points laying in the plane, I'm going to draw, at the beginning, they're all in the root, and then I'm going to draw a cut, and this is going to put some points on one side and some points on the other side. And then I'll continue to recursively do this. I'll make another cut. This further splits up the points. And then I'll continue cutting the points up further and further. Sorry, this keeps double-clicking, until they're all in their own leaf cell. Once they're all in their own leaf cell, now I have that's the end of the embedding, more or less, is that that's where they end up. And now I need to now define edge weights to make this symmetric. So this partitioning scheme right here is the same scheme that's used for all three algorithms I told you about. So what's the difference? There's only one difference between these three algorithms, and that's how you actually define the edge weights of this tree. So formally, what's actually going on is all three algorithms are imposing this randomly shifted grid, where you shift a grid and recursively you cut the grid the side length of the grid in half on every step. So you start with the whole thing, then you ut it to delta over 2 to the I, delta over 2 to the I plus 1, and so on. And you had this recursion tree T. So in Piotr's paper, he set up the edge weights to be such that they were the worst case diameter of a grid cell. So if the side length was delta over 2 to the I, it was like delta over 2 to the I times D. So that's why you got this non-contraction with deterministically, because it was actually the diameter of a cell. Then in Andoni, Indic, and Krauthammer in 2008, they used a value which is the distance you would expect points to be at over the random cuts. So now there's like a two-sided error thing going on, but because of that, you get the D now disappears from the approximation. But the important point is that this distance from the AIK paper, it's still a fixed quantity. It doesn't depend on any data. It just depends on the depth of the tree. It's fixed, like data independent. And then the main insight of this paper in 2022 was that we can get a better approximation if we set up the weights to actually depend on the points which went down an edge of the tree. So in particular, we set it to be this very well-defined concept. So every vertex of the tree is some piece of space, and there's some points like that went to U from our data set and some points that went to V, the child. And so the way I'm going to define the weight is just sample a random point from the parent, U, sample a random point from the subset, child, V, and look at their distance. And look at that maybe an expectation over this random sample. This is a simple thing to compute. You can estimate it very efficiently. You don't even need to compute the exact expectation. And so this is a succinct and efficient thing to compute, but it somehow models more accurately what the actual distances between points were. And the main result of that paper was that using this one change, just changing the edge weights, you get a better approximation. You get this log number of points that you're embedding approximation. So that was the main result of that. So now, we'd hope to try to use this. We want a log S approximation for nearest neighbor search. That was the goal of this talk. So we'd hope to use this embedding to get a log S approximation for nearest neighbor search. Well, there's a lot of pros of this. We get this better distortion. So whenever the universe size is poly S, we get this better distortion, and it's still concise and efficient. But there's two key issues with this. The first is that this embedding is only actually defined on this point's omega. So when your query comes, you didn't know your query in advance. So somehow you can't define the mapping on the query before you know the query. The second issue, and this is probably the more challenging issue, is that in nearest neighbor search, I have n sets of size S each. If I wanted to use this embedding, I'd have to set omega to be all n sets of size S. So now my approximation is going to be log n times S, and that's much worse because I didn't want any n. N is like significantly larger than S. So if I don't want this log ns distortion, I can't actually run this on the entire data set. I need to do something else instead. So here's the main idea. The main sort of subroutine is this simple structure that we're going to call sample tree. And the idea is, well, hey, I know I can't afford to define this data-dependent embedding on all n times S sets. If I want a log S approximation, I might as well only run it on S sets. Which S sets? Well, let me sample a random poly S sets from my data set and then define the tree embedding, the data-dependent tree embedding on that random sample. And I'm going to hope that random sample is representative in some way. We'll see what I mean by that. So here's the algorithm. Create the same quadtree embedding tree partitioning scheme as before. Sample omega random poly S points from the data set. And now I'm going to define the hybrid weights. I want this mapping to be well-defined on all the points in the metric space. So what are my weights? Well, for an edge UV, if one of my sample points goes down that edge, well, then it makes sense to define the edge weight, the data-dependent edge weight. It's a well-defined thing. So then I just use this edge weight from the CJLW paper, this data-dependent edge weight. But if no point goes down the tree, then this thing is ill-defined. These two sets are empty. There's nothing in the set. So what can I do? Well, I'll just revert back to the prior AIK paper. and I use these data independent edge weights, the fixed edge weights that don't depend on the data. So these hybrid weights, if I can define the data dependent embedding, use that. Otherwise, use the data independent. So if you look at this tree here, if x1, x2, x3 is your sample, then all the edges that one of these points went along, I can use the orange data dependent embedding. But for all the other edges, these dotted edges, there's no sample went down them. So I have to just fix the data independent fixed value as the edge weight. But now I have a bona fide embedding of the entire space. It's now defined on all possible points in my tree. And so now I actually can talk about the embedding over the entire metric. So let me briefly talk about what is the distortion we get for this. So that's what we really want to understand. So if I have 2 points, x and y, suppose that they were in my sample. What is their distortion under this embedding? Well, their distance in the tree is only going to use these data-dependent edge weights because they both were part of the sample. So I'm going to inherit exactly the same approximation guarantee that the CJLW paper had. I'm going to get this log S approximation. So it's fantastic. For points in the sample, I do well. There's no new theory is needed. On the other hand, what about 2 points that are very far from the omega? If 2 points are in the tree and they're very far from any sample, then their path in the tree may only use data-independent edge weights. In that case, they're going to inherit exactly the guarantee from the AIK paper, which is log squared s. So that's worse than what we wanted. So we already know this isn't going to be enough on its own, because for points that are very far from the sample, they're going to get a worse approximation. But the point is that omega was kind of randomly sampled. So the hope is for most points, they're somewhat close to omega. And we're going to hope to use that. So in particular, what I'm going to hope to show is that for points x, suppose they weren't in the sample, but suppose they were close to some point z that was in the sample. I know that I get good approximation for z. Can I extend the approximation guarantees to a small neighborhood around z? I want to show that the good data-dependent embedding guarantees hold for points that are close enough to a sample. That's the main technical challenge of this paper. And for points that are too far away, we'll do something else. And so the main result is what we call this extension to a chamfer neighborhood. So we want to prove something of the following form. If 2 sets A and B are close to the sample, then their earth mover distance in the tree is a good approximation of their original earth mover distance, a log S approximation. This is the kind of result we want to prove. And I need to tell you, what does it mean for a set A to be close to the sample omega? Well, I could use earth mover distance as a measure of similarity, but this is actually a little bit overkill, because it turns out that all I really need to do is take every point in A and sort of look at how far it takes to move to the nearest point in omega. I'm not actually matching it to omega. I'm just using the weights in omega to give me a better approximation. So we use a weaker notion, which is called the chamfer similarity. And the chamfer similarity is not even actually a valid distance metric. It doesn't satisfy triangle inequality, but essentially just says for each point in A, move it to the nearest point in B and sum up those distances. And that's the chamfer similarity. And this is what we're going to use to measure distance to the sample. So what we prove, this is one of the main technical results of the paper, is that we can extend the guarantees to points that are near to the sample in a chamfer neighborhood. So formally, what we show is for 2 sets A and B, how much do they expand? What is the expansion in the tree? It's at most log S times their original distance. Remember, that's sort of the guarantee that we wanted, times this additional factor. What is this additional factor? It's log of the chamfer distance from the set A to the sample omega divided by how far is A from B in earth mover distance. So in other words, the extra approximation is how far is A from the sample versus how far is A from B. So if A isn't too much further from the sample in chamfer than it is from B in earth mover distance, if it's at most polylog S further, then this is a log S factor, and then we're fine. We wanted log S times log S. So in other words, if this ratio is almost some polylog S, then we get a good tilde of log S approximation. And I won't really have time to go through the proof, but the main idea is like the key place where error actually comes into play. So if I have 2 points, A and B, that want to be matched together, and I have some sample omega from the set, once these points move up to the tree and get to the edges that omega went through, now they're getting good error because omega had those data-dependent edge weights and the error from those data-dependent edge weights was good. So the issue are points where A and B have already met, but they haven't quite met together with this point omega. And what we show is basically the number of such edges is log of the ratio between the 2 distances. And that's where you get this log term from. So I don't really have time to say more than that, but essentially what we do here is we now have a sort of a case-wise analysis. this whole thing, what we were just trying to show is that for points that were sufficiently close to a sample, we get a good approximation for them. But what about the points that are super far? That could happen. So what we show is that actually if a query is really far from the set omega, then actually, this prior Andoni, Indick, and Krautskammer paper, it gave a log squared s approximation. But log squared s approximation is enough to tell the difference between 1 versus log 10s. So even though the approximation is not log s, it's enough to tell the difference between this huge log 10s factor away. So for queries that are very far from the sample, we use the prior work. For otherwise, we use this embedding. And then we have sort of a gluing procedure to show that they can be glued together into one single algorithm for the nearest neighbor search. And this is the full thing. So I think I'm a little over time. I want to jump to just briefly say a couple things about open problems. So the first thing we could naturally hope to do is we saw what you could get for L1. You can get this 1 over epsilon versus n to the epsilon query time. The hope, could we do that for Earth mover distance? And it seems very challenging. There's a lot of reasons to believe that tree embeddings themselves actually are formal reasons are limited at this log s approximation. Actually, in the paper, again, I haven't defined what LSH is, but there actually is, at the end of the day, a locality-sensitive hash function here. And we actually prove a lower bound by showing that these hash functions that have a certain property, that close points collide with some at least constant probability. Let me say that almost all nearest neighbor search data structures have this property. They cannot get better than they cannot actually get this constant approximation. So, in other words, what we've ruled out here is we've ruled out a large classes of approaches to get a constant approximation, but we haven't ruled out the possibility entirely. And the last thing is something I haven't talked about at all, but some of you may be familiar with the sketching model. Alice has a set A, Bob has a set B, and they want to compute the Earth mover distance between A and B with communicating a small number of bits. It turns out that the best we actually know is log squared s for this. And there's questions like, can we get it down to log s? So like the picture of sublinear Earth mover distance, we have sketching, we have streaming, and we have nearest neighbor search. What we just showed is you can actually get log s for nearest neighbor search. In a paper a couple of years ago, actually this CJLW paper, we showed that in 2 passes you can get a log s approximation in streaming. In 1 pass, it's still the best known as log squared s. But for sketching, the best known is log squared s. So can these 2 things be made log s? It seems like plausibly, but it doesn't follow immediately from what we know so far. So those are the main things that I would leave to you all today. So thank you so much for your attention.
Sorry, that's probably a very dumb technical question, but so what's the intuition behind something poly S? Because S is just the size of a point, right? It's not the number of points. It feels like right now, like the way you introduce it's like, oh, that's all we can afford, so that's what we're gonna do. But
yeah, so I think your question relates to a couple of things I've done. Maybe just like in particular, why is poly S the right cutoff here? So one thing to note is that, like, I guess one way of answering this question without actually diving into it is that almost all of the comparisons are sort of on a set-by-set basis. Because when we do nearest neighbor search, I just need to like eliminate a constant fraction of the points on every step. So a lot of these things are not like ever doing a union bound over n points. It's just looking at like 2 pairs, 1 point and another point, and saying, suppose they're like far from each other, what actually happens between the distance between the 2 of them? And the reason that and then from there you only have like s points. So a lot of those arguments end up boiling down, like the translation between embedding 1 point to a tree and s points. The reason you get this log s is because you're doing a union bound over s squared things. That's where the log s comes from. And it turns out that you only need to consider 1 set at a time when you're doing this comparison. The reason that log 10s here is the right threshold. I mean, in some sense, you just need it to be some log factor. Like do you have a succinct way of saying why that is?
So each sample has s points. So this is the difference between s log s and log s.
Wait, I mean, yeah. I mean, also, we just want this to hold for like the omega is like a sample from and we just, because we need this data dependent guarantee, we just need like 99% fraction of the data points are close to omega under this guarantee, under like a specific threshold, like r times this. And so that's what you would be able to show. That's yeah, I think that's, yeah, I think that's more or less the intuition. But why it's not a larger value, yeah, I don't think it's clear to show in from this slide.
Maybe one more.
Good.
Yeah, I'm wondering for this chamfer extension lemma, how important was it that it's chamfer distance? Like instead if I try to look at the maximum distance between like a point in A and its nearest point in omega.
Okay, so yeah, it's important that it's the chamfer distance is the sum, right? So that's important. So like, the way that you prove this lemma is you look at the matching from A to B, and you're like, I could try to. So here's like a trivial way to try to prove this lemma. I could say, let me first look at how far it takes from me A to go to the nearest point in omega. On those edges, I'm going to be going on data independent edges, so I'll get a log squared s approximation. So I'll pay log squared s approximation to move to omega. So it'll be log squared s like chamfer distance from A to omega, and then plus the B to omega. Once I've moved A and B to omega, now they're both living in omega, and so they can now use the data dependent weights to match together very nicely. So there's a weak version of this that says move to omega and then match in omega. So for that, you need to like at least walk each point to this nearest point in omega. To get a better bound, so there you would get like log squared s times the chamfer to omega plus log s times the distance. So that's actually not good enough. The way you do this is a similar idea where you look at the nearest point omega to A, and you look at how far away was it from its matching point in B. And the further away from it, the more extra factor approximation you pay. But you need to do this for every single point in A. So it's important that it's the sum of points. So this is, in some sense, it's the weakest thing. I mean, maybe you could prove this for Earth mover if you use the Earth mover distance or some measure. Probably not, because omega is a much larger set. But in some sense, I think chamfer is really you're trying to model how far does it take to move one point in A to the nearest in omega, and that's chamfer.
So let's make the rest of the questions offline. Let's